Hi, so we are looking at the section 4.2 problem number 11. So if you haven't done some approximate area under the curve problem, so like number 7, you're going to want to do those first before you get into this one, because this kind of builds up to it. So if you watched the previous video for exercise 7, you used rectangles to approximate the area under a curve. Now what we're going to do is we're going to take that a step further, and we're going to find the exact area of the curve by looking at having an infinite number of rectangles, each with that width of essentially 0. So we're getting our width smaller and smaller until it is actually 0, and we have an infinite number of rectangles. And obviously we can't do that with discrete math, but we use those limits to approximate what's the trend. So that's where we go from here. So kind of an idea of what we can expect. So we want to divide this into an infinite number of rectangles. And so our delta, actually, let me switch colors. Our delta x is just going to be 1 over n, because essentially we're going to start looking at the limit as n goes to infinity, which would mean that our width is 0 and n is, looking at what happens as n gets larger and larger and larger. Then, you can see each of these graphs work really well, and we could certainly sketch that. But it is just a line. And we've got a negative slope of 4. And I think these visuals do a pretty good job. They're all kind of consistent. And we want to look from 0 to 1. So we're not finding the full area under the curve, just from 0 to 1. So I'm, exaggerating. My sketch is never going to be perfect. All right. So let's go ahead and examine some things. I'm going to make a rectangle. So the width of this rectangle is going to be that delta x. It's going to be that 1 over n. And then the height of it is going to be the corresponding f value. So we'd want to find, the function value evaluated at wherever our line is. And since we're starting off with 0, then we have these lines. The height of each of these, we're increasing. And we are looking at, we have 0 plus 1 over n plus 2 over n plus 3 over n, and we're continuing that pattern until we get to 1. And that's how we divide it up into n rectangles. So what we're really looking at is the limit as n goes to infinity. We're going to take the sum of each of these rectangles. Their height is going to be this f of, we'll start off with our counting indice, I over n. And then the width of each of them is going to be that 1 over n. So this f is our height, and this 1 over n is our width. So we have a height times our width, and then we're taking an infinite sum of those, because we're looking at it from I equals 1 to n. Okay. And then we want to start substituting some things into our function. So this becomes the limit as n goes to infinity of the sum from I equals 1 to n. Our f of x is this negative 4x. So we get negative 4 times I over n plus 7 times this 1 over n. Now, the 1 over n, you can factor out of the summand because it doesn't actually affect the summation, right? N is a constant, ideally. It does affect the limit, so we can't factor it out of the limit, but we can, just to make it a little bit easier, write this as the limit as n goes to infinity of 1 over n times the sum, I equals 1 to n, and then distribute this 4 negative 4i over n plus 7. Okay, and then from there, if we're looking at the sum, this negative 4 over n, that's a constant. So we're just really looking at the sum from I equals 1 to n. So we have the limit as n goes to infinity of 1 over n. And then when we apply the sum and rules, we have this negative 4 over n, the sum of just I from I equals 1 to n. And so that's going to be n times n plus 1 over 2. And then the sum of just that constant from I equals 1 to n is going to be plus a 7n. Okay. So we've got a lot of things going on. We can start kind of working with some of this to simplify. So we've got the limit as n goes to infinity. We can distribute this negative 4n. So we get negative 4n squared minus 4n all together over, and then we can also distribute this 1 over n. So we end up with 2n squared for that first term. And then we distribute it to the 7 as well. We have plus 7 over n squared. Now looking at this limit, we are able to simplify some things. So we're looking at the limit as n goes to infinity. We have a common factor of really n squared. So we end up with negative 2. So that negative 4 over n, that negative 4n squared over 2n squared, that becomes a negative 2. And then we have that negative 4n over 2n squared. This is going to be minus 2 over n. And then we have plus this 7 over n squared. Oops. You know what I realized over here is this shouldn't be 7 over n. This should have been 7 times n because we're adding a constant. So this will be 7 times n. And that's going to affect this. So you'll want to make that change in your notes. I apologize for that. 7n over n. This will be a plus 7. Again, I apologize. So kind of highlight that. Maybe even you were watching as I made that mistake. But yes, this right up here, the sum from I equals 1 to n of 7 should be 7n. So fix that. That should be a 7n. And then when we distribute that 1 over n, this just becomes 7n over n, or 7. And then this becomes negative 2 minus 0 plus 7. And then we get a positive 5. So the area using limits is that positive 5. And then looking at the sketch that we want, we kind of sketched our own. The y-intercept should be when x equals 0, we should have a y-intercept of 7. So that's going to rule out this one because these have a y-intercept of 5. Okay, just for the upper function, these have 7, 7. That's good. Go from 0 to 1, 0 to 1. And then the other point is when x equals 1, we have the point 3. So that looks to be this one right here. All right. So yeah, like I said, just make a note of that error, and then we're good to go.